Today in section 5.3, we're going to do something a little bit different. Instead of me throwing a bunch of definitions and theorems at you, we are going to focus mainly on trying to solve a particular type of problem, frequently called a least squares problem. This one example of this kind of a problem is trying to find a line that passes through some given points. This is a common thing to do when you're trying to analyze data collected from some sort of experiment or some real world situation. If we have a situation where we have, say, 2 data points, it's really easy to find a line that passes through both of those points. But if we have a bunch of data, so more than 2 points, so we have, say, this point here, here, something like that. It's highly unlikely that we're going to have a line that passes through every single point. If we try to connect those with lines, we're not going to get one line. In many real-world situations, this does not mean that the data does not have a linear relationship, but it might just be due to experimental error that the data doesn't quite exactly fit a line. In these situations, we'd like to find a line that is close enough, that the so-called line of best fit. So it's easy to imagine that we have a line here that's really close to all these points, and so maybe the fact that they're not on that line is just due to some error. How do we make this idea precise enough to actually find that line, though? How can we actually get a problem that we can actually solve? So let's set this up by starting with a linear system, ax equals b. We're going to assume here that this system is overdetermined. In other words, we have more equations than we have variables. And this is basically the idea that we have over here. We had too many points to expect to be able to solve for a line. We can't expect our line to hit all those points. That means that if A is an m by n matrix, then m has to be bigger than n, because m is our number of equations, n is the number of variables. We're going to define a function that the book calls the residual. This is going to be the difference of b minus a times x. So for any vector x that we plug in here, it's going to be this difference. And this is going to be a measurement of how far x is away from being a true solution to the system. We'll go ahead and take the magnitude of this thing. So this is the magnitude of the difference between b and ax. As a magnitude, this is always at least 0. It's always 0 or bigger. And if it ever does equal 0, the x where it equals 0 is an exact solution. But we don't expect an exact solution, so we are really more interested in trying to make the magnitude of r of x as close to 0 as possible. In other words, our whole goal is to minimize the magnitude of r of x. Or sometimes we'll put the magnitude squared if we rather not have any square roots show up or anything like that. But the method that we're going to be using here isn't going to be dealing with square roots in the first place, so we don't really need to worry too much about that. A vector, which will frequently in this section denote as x with a little hat on top of it, if x hat is a vector that minimizes the magnitude of r of x, we call x, or x hat, a least squares solution to the system ax equals b. That's what least squares means in this context. It's just a minimizer of this function. if x hat is a least squares solution to our system, then the vector a times x hat is a vector, we'll call it p, that is in the column space of A. And so we're trying to find out how close the original B is to the column space. How close is it to the set of all possible P's? So that's where we have this theorem, Theorem 5.3.1. It's basically saying that if we have a subspace of Rm, for any other vector B that's not in our subspace, there is a unique P in that subspace that is the closest possible to B. And in fact, that this is the unique P that makes B minus P be in the orthogonal complement of S. And to put this in easier terms, what this is really allowing us to do is drop a perpendicular from a point onto the subspace. So if we imagine our subspace here as some plane in three-dimensional space, we have our B represented by this point here. We're just dropping a perpendicular down and getting a point P that is the base of the perpendicular. B minus P in this case is the vector that points from P to B, and it should be perpendicular to everything in S, every vector that lies in S. And so that's really all that we're trying to do here. But how do we actually prove this? Because we'll go ahead and prove this one theorem. Or, well, we'll prove both theorems that are in this section. Because there's not as many theorems in this one as there have been in the last couple. But let's actually use the stuff from last section. Remember that any Rm, for any subspace, can be decomposed into a direct sum of that subspace and its orthogonal complement. That means that we can write B, so we're starting with this B, but we don't have P yet, but we'll assume that B can be written as P from S and Z from the orthogonal complement of S. The fact that Rm is a direct sum of these means that we can do this, and in fact we can do it in a unique way. This P and the Z are unique to this B. If Y is anything else in S, here Y is not P, then we can go ahead and see how far away B is from Y. Or actually, we'll go ahead and square this. Now we'll do a little bit of trickery, try to kind of insert P in here. Essentially, we're going to add and subtract P from the inside, and we'll get a B minus P plus this should be a P minus Y. If we just expand that out and we cancel the P's, we'll just get the B minus Y that we had over there. That's still squared. Okay, so where does this leave us? Well, remember that P minus Y, that's the difference of two things that are in S. So P minus Y is something in S. B minus P, well, keep in mind, what is B minus P? But it's just the vector Z. And Z, we assumed, is in the orthogonal complement. So this is an S, this is an S perp. They're orthogonal to each other. And we had a Pythagorean law that said if we have two vectors that are perpendicular to each other, and we take the magnitude of their sum and we square that, it's the same thing as if we take the sum, or the sums of the squares of their magnitudes. You can just basically pull that apart. Now, what does this mean? Well, keep in mind, we said that that Y is not equal to P. That means that P minus Y has a magnitude that's bigger than 0, strictly bigger than 0. So This, the magnitude of b minus y, equals the magnitude of b minus p plus something that is bigger than 0. And so the magnitude of b minus y has to be strictly bigger than the magnitude of b minus p. That means that p has to be the biggest, p has to be the thing that is in S that is closest to b. Anything else we just showed is further away. And p is specifically characterized by the fact that the difference of b and p is an element of the orthogonal complement that is perpendicular to everything in S. And that's exactly what this theorem is saying. So we can go ahead and put a little box saying we are at the end of our proof. That's a full proof of it. Maybe with a little bit of more wordiness to write it up, but that's the full proof. We're going to call this vector p the projection of b onto the subspace S. We take our b and we project it down to the subspace. If we're dealing with just two vectors and we're projecting one vector onto another, this will agree with that definition if we assume that what we're doing is projecting onto the subspace spanned by the second vector. So if we have our vector b here, and we're projecting onto a vector p, we're really thinking about the entire subspace that p makes, and we're projecting down onto that subspace. So really, we're not making a new definition. We're kind of generalizing the old one, but giving a nice broader context. We can project onto any subspace without any trouble. Or, well, this doesn't give a way to do it, but that's what we're going to be talking about through the rest of this video. So let's return to our system ax equals b with least squares solution. So least squares solution x hat. And we're going to say that p is a times x hat. We want to project b down onto the column space of A. So here p is in the column space. Remember, we denoted that as R of A. And by that theorem, that means that the difference, b minus p, which is really just b minus a times x hat, or in other words, r of x hat, remember our residual, this vector needs to be perpendicular to the column space, just from our last theorem. So this is in the orthogonal complement of the column space. But remember, in our last section, we showed that this is, in fact, the null space of a transpose. So really, what we're saying is that we want this vector, or you could say r minus p, or sorry, not r, b minus p or b minus a x hat to be in the null space of A transpose. In other words, if we take A transpose times b minus a times x hat, we want that to equal 0. We can rearrange this a little bit, basically distribute the A transpose to each of these terms and move stuff around. We get down to the equation A transpose A x hat is equal to A transpose B. And note that an interesting thing has happened here. By taking A transpose times A, this is the product of an n by m matrix and an m by n matrix. This is now a square n by n matrix. Over here, we have an n by 1 column vector, because we have an n by m times an m by 1. So what we've taken our overdetermined system and we've changed it into a square system. That makes it a little bit easier to solve. It's much more likely that a square system will have a solution, and it will have usually will have a unique solution. Not guaranteed, but very frequently. So we're in a much better state at least. If this has a solution, and that's going to be the least squares solution that we are looking for, we are going to refer to this equation here as the normal equations. Equations because it's really a system of equations. The normal equations for the system ax equals b that we started with. So how can we tell whether or not the normal equations actually do have a solution? Well, this theorem here gives us our answer. Theorem 5.3.2 says that if we have an n by n matrix of rank n, this is our key point here, this condition here that is rank n, then the normal equations that we wrote before has a unique solution. There's a unique solution, and they wrote it out here as x hat is in terms of the inverse of A transpose A times A transpose B. Technically here they are saying that this matrix does have an inverse. That's not something we knew before, but something we'll show in a moment. And then we have a unique least squares solution to our original system. So let's actually go ahead and prove this. But first I want to mention here, A being of rank n, that is as, well, because n is less than m is the bigger of these two, A couldn't be of rank anything bigger than n anyways. What rank n means is that the columns of A are linear independent. We might say here that A has full rank. It's as big as it possibly can be. And so you'll frequently hear people say it has full rank, and so we can actually find a least squares solution, or at least a unique least squares solution. It's possible to have a least squares solution even if it's not full rank. We're just not guaranteed one. So let's prove this one. So obviously, because what they want to use the inverse here, we want to show that so want to show A transpose A is non-singular. How do we do that? Well, it's a square matrix. So what we need to do is show that the columns are linear independent. Or in other words, we want to show, we want to start with a solution to the equation A transpose AX is equal to 0. If we can show that x has to be the 0 vector, then that will show that A transpose A is in fact non-singular. That was one of our results from back in probably chapter 1. Well, what does this actually mean? The fact that we take A transpose and we apply it to AX, that means that AX has to be in the null space of A transpose. So AX is in the null space of A transpose. But we also know that the null space of A transpose is the column space of A perp, the orthogonal complement of the column space of A. However, what is this vector? It's A times something else. A times anything will give you a vector that's in the column space, pretty much almost by definition. Here is basically as if we just took the columns of A and added together a bunch of multiples of them. So AX is always going to be in the column space of A. So we have a vector here, A times x, that is both in the column space and in the orthogonal complement of the column space. Well, we know that if something is in a subspace and its orthogonal complement, then that means that that vector has to be 0. Or, oops, a times x has to be 0. So we've kind of taken the A transpose out of our equation. We've reduced it now to ax equals 0. Here's where the fact that A is of rank n. Remember, that means that the columns of A are linear independent. What do we have here? We're saying this linear combination of the columns of A equals 0. If x was x1 through xn, we're just taking x1 times the first column of A. I don't know, put a little hat over that to say it's the first column, and so on and so forth. Should be xn, an. We have this linear combination of the columns of A equals 0. If they're linear independent because it has full rank, that means that all the x's have to be 0. In other words, the vector x equals 0. So we started off with this equation here, and we showed that the only possible solution to this is x equals 0. So A transpose A is non-singular. And so we're basically just allowed to multiply each side of this by the inverse of that matrix. So here, A transpose AX equals, sorry, we need A transpose here, B. If we can basically multiply each side by the inverse of this matrix that's in front of the x, we can cancel it out on this side, and then we're just left with it. We're left with the inverse times what we originally had on that side. We end up with this very explicit solution to that system of equations. Okay, so that is going to be our least squares solution, which we might as well just call it x hat now, because that's what we want it to be, or that's the notation we've been using for it. And we've basically found a way to solve the system. Now we're not going to go through all these steps every time we solve one of these. So pay attention in the next video where I actually go through how you want to approach doing the problems yourself, not having to reinvent the wheel every time. But I do want to mention that what we've done so far has actually led us to a couple of other definitions. Remember that since this vector p that is A times x hat is the projection of B onto the column space, well, what does that mean? Remember, x hat, if we go ahead and replace it in here, is A transpose A inverse times A transpose B. We can find that projection P from B by multiplying by this matrix here. In other words, if we give this a name, we're going to call it capital P. This is a matrix that takes any vector B and returns its projection in the column space, or projecting that vector B onto the column space. We're going to call this a projection matrix. And there's various properties that you can talk about with projection matrices. And if you want to, you can go through some of the exercises. I'm not assigning any of them, but it's something that is fairly well studied. It turns out that for any subspace, we can find a projection matrix. In fact, if we find a basis for our subspace, we can use that basis to form this matrix A, and then use this same formula to actually get the projection matrix. That's a little off topic for what we're wanting to do right now, but it's still a very useful idea. The other thing might want to talk about is that since x hat is found by multiplying b by, so let me just write it down here. X hat is A transpose A inverse A transpose B. We basically find x hat by multiplying b by this matrix here. Then it's almost like what we've done is solve a square system. If we had a different a and a different b over here, we can, and our a is non-singular, then we're solving our system by just multiplying by the inverse. This matrix here is basically playing the same role. It's not really an inverse, but sometimes it's called a pseudo-inverse. So that's what we call the pseudo-inverse of A. Sometimes denoted as A+. It is an n by m matrix. Remember, A itself was m by n, so we've actually swapped the order on that size. And it has the property that A plus times A is always the identity matrix. Specifically, the n by n identity matrix. But A times A plus, so the other order, is not going to be the m by m identity. Because, well, it has to do with the fact that m is bigger than n. Essentially, there's not enough that's in here that's linear independent to make m different linear independent rows or columns. So we actually can't get that unless A was a non-singular square matrix to begin with. It's kind of worth noting here that this is our definition only for overdetermined systems where the A is full rank. In general, there are other definitions for what we can call the pseudo-inverse that has certain other properties that make it useful. But this is something that some people talk about, and it's most. I don't really know of any other situations where it's too useful. It's just very useful for these kind of problems. So, kind of getting a little off topic, but I felt being able to actually talk about what a few of these things are, how people talk about them, all that kind of stuff would be kind of useful. But that's all the theory. Join me in the next video for how we actually approach solving these kind of problems. And that's probably actually going to be more useful to you, especially with their homework. So I'll see you then.